going to, all right. I want to talk briefly about the assignment itself. Actually, I think I saw the mic moving. Yes. Just want to be sure. I forget the due date for this. It's on Canvas, and it's not for a little while, again, because this lecture wasn't supposed to be today. Actually, it was supposed to be today, but if we skip MSDs, then, then we're on the right schedule. And because this has an assignment, there's an assignment for applied physiology, then it's important for us to talk about this now. So it says typed. I'm okay with you submitting it a hand copy. What you can type, I would like you to type. And if you are working things out, equations out by hand, then you can do that. However, I highly recommend using Excel. And I'll show you how Dr. Fogelman had set up it's in the slides, but we'll see how he had set things up. And I'll show you what a couple of the equations look like in Excel, so you have an idea. They're not, the equations look scarier than they really are. I mean, they're straightforward, they're just long. Okay, so it's just take your time, pay attention to the detail. That's why I want to definitely do this one in person and not just record it online.
Professor Gallimore says, attention in us, not good.
Well,
I remember something.
Well, I mean, I say attention to detail. Take your time. Like, don't rush through it. List out all your variables and what they equal. I like to have a little sidebar or something where I have all my variables listed out to refer to, stuff like that. Like, just being methodical instead of trying to rush. If it's like 11:30 that night before it's due, you're not, right, it's not gonna work.
I think we're gonna need to take another 10 day on this one.
So it's going to be, a lot of it will be typed, but there is math involved. These first couple is just describing the job cycle. And what I mean by that is the tasks involved with performing a certain job. What I would like, and so what I would like is patterned after what we're going to see in the lecture slides, but I'd like at least 4 tasks in this job cycle. And I would like at least one of the tasks, preferably 2, to be different from the tasks covered in the lecture slides. So at least one has to be different. It could be very similar to what's in the slides, but something has to be different about the job. Well, you will have different numbers for sure, but no, one of the tasks. I would like one of the tasks. So there are equations for each different task.
Can it be any job?
Yeah. What I would prefer is you imagine something that either you have done in the past for a job, or you are doing, or just something that you're familiar with. And so just to use this one as an example, you lift the box from 0 centimeters. So this is a lift from the floor up to 75 centimeters. Carry the box for 10 meters at 2 meters per second. So the time is an important part. Keep track of how much time you think stuff takes, and the speed of walking maybe. Place the box on a 1 meter high shelf, and then you go, like in the lecture slides, the example is that you go back to get another box. So the walking part, and that's a complete cycle. So that would be a cycle of 4 parts, something like that. List out the variables. So the subject, so if you're a female subject, body weight of whatever in kilograms. Height is also important, but for different reasons. It's not like biomechanics. But if you're lifting to your waist, for example, then just take like take 50% of your full height, and that would be the 75 centimeters to your waist height. Again, it's a little more It's not like biomechanics. We don't need it for the same reasons, but describe the task. You'll talk about it how you would normally, like in a discussion, but then also use some of the terminology from the class. So it's a stoop lift, for example, and then also, well, describe the task and then indicate what equation you're going to be using. So just list out the equation, and this will be helpful for also doing it because you'll list out just the equations that you need to the specific tasks that they go with. And here, illustrate your work. If you're doing this in Excel, which I recommend, just copy and paste what you have in the table into here, into, the document. That can be showing your work. If you want to do it all by hand, then you can either scan it and submit it on Canvas or bring it to class before the bring it to me before the due date. Describe the postures involved. So postures are important in applied physiology, and they affect the equations. And it's all about energy. So we're looking at the energy expended to do these different tasks. So each posture will expend a different amount of energy. And then, so these equations are part of Garg's method. There's a summary equation that puts all of them together, but you're going to estimate the energy expenditure for all of the tasks, and then you kind of put them all together with the postures, and it will give you a number. And based on that number, you use a little chart. I'm guessing that's Romer. I don't know. Looks kind of, maybe it's French, maybe it's not. If it's German, then I don't know how they would say that. But anyway, Romert. So he has a little table that you use to determine how much time in a 1 hour period should be dedicated to taking a break, to resting. So you can imagine for light tasks, it's not going to be very much. 5 minutes, 10 minutes, 15. For intense activities, it's going to be a lot, up to 45, 50 minutes, or even it might say, don't do this. You should not do this task. So I'll change that around then. Okay. Yeah, that's interesting. Yeah, I think I was following his schedule. But adjusting it for our semester. But that lecture doesn't come till after this one. So I'll adjust that. I might move this one up a little bit, and I'll move that one back. Thanks for pointing that out. Yeah. So again, it doesn't need to be more than 1 or 2 pages. And that's like, if you have some nice figures, then it'll be 2 pages, which it would be nice to have some nice figures, but you don't need lots of text. Just enough to communicate what you need to in a logical way. So, sweet. So like I mentioned, applied physiology is all about the energy. When we think of ergonomics, there are generally two key components. There's the biomechanics, so the forces applied to different joints. And I'm going to see if this... Yeah, it has this little USB spot, but I can't get it to work. So come on, Microsoft. All right. They're good at some things. All right. So none of that. That's okay. So we're going to talk about work design just a little bit. Work rest schedules is kind of the point of the assignment. So you're going to determine what sort of work rest schedules should someone performing this have? How much rest do they need if they're doing this task, for an hour or all day? And we'll talk about energy expenditure, a little bit about VO2 max, and then Garg's method. I hope I'm saying that right as well. We've talked about static versus dynamic a little bit. One thing that I want to point out here, is that we haven't talked about, is that it's a function of the intensity of the work. So if you're doing something that's static but very low intensity, you can, like holding your arm out, you can last a while. It's not nearly as bad for you as if this is something more intense. You're holding a heavy load in a static position. For dynamic work, with static, it's usually localized fatigue. So the muscle or muscles that are involved are going to be the ones that get tired and start to hurt. With dynamic work, it tends to fatigue your entire body. And but because of the blood flow that we talked about, you can usually endure and last a lot longer because your body can deliver oxygen, clear out any lactic acid, and keep going.
The static was the one when your muscles were constantly being flexed or not flexed.
Yes, yeah, contracted. Yep.
Like you're holding something out.
Yeah.
Yes. Yep. So static, bad. Dynamic, good. Although while it does result in more generalized fatigue of your full body, you can last longer and it's better. We're designed for that kind of work and not to just sit and hold a certain position. And that fatigue is related to maximum oxygen consumption. So we will, in a couple more slides, we'll get to some old school photos of what you sometimes see in commercials, I think, where they have an athlete on a treadmill and they're all hooked up to all this, there's something on their face and all this other stuff.
Probably working out to go into space.
Well, yeah, so astronauts do that too, but one of the things that they're measuring is VO2 max, and we'll talk about that. All right, so AIHA has some recommendations on work rest schedules. Their method only allows for a range of 4 to 8 kilocalories per minute. And we'll see the example that we're going to go over is in that range, so we can use it. But if you do an analysis for a task that is outside of 4 to 8, then you won't be able to use this. And that's fine. You actually, for the assignment, you don't need to. But what you do is so M is that metabolic rate of hopefully between 4 to 8 kilocalories per minute. You divide it by 4, subtract 1, and then multiply by 100, and you will get a percent. So there's a small example here. If we estimate a task or a job cycle to have a metabolic rate of 6 kilocalories per minute, and it'll be 50%. So I want to do that real quick. So 6 divided by 4, it's the same as 3 divided by 2. It's going to be 1.5. Then we subtract 1 from it, so it's 0.5.
Which makes 50%.
So it makes 50%. So that's how that works. Nice and easy. So yeah, so we get 50%. This portion is termed P. And then we just multiply 100 to get a percent. So P equals 0.5. Now, to determine the amount of time that should be dedicated to work, you plug it into this. So I'm not totally sure why, but that's what you do. So you add 1 to it. So you actually take it back to this right here. Add 1 and then divide 60 by that number. So if we add 1 here, it's going to be 1.5, which is what we started with right here. And then we do 60 divided by 1.5. And when you do that, you get 40. So 40 minutes for work and 20 minutes for rest. That's how theirs works. You're not required to do it for this assignment, but just keep that in mind in case you do need it later. This is Romert's figure, his graph. And later on, we won't have it quite so large. I apologize for you not having your notes. It's okay, though. I mean, we're not going to be doing tons outside of what's actually on the slides. So what you would do is, after you've estimated the kilocalories per minute, that number will correspond to one of these: light, moderate, heavy, very heavy, or extremely heavy. So up here it tells you what, where each one fits. So if you are doing light work, for example, you look at the lines that are crossed. If you were to just draw a line, actually light would be right here, but you would draw a line straight up and then determine, you look at these lines, it could be any of these, but usually you go with the max. So in a 60-minute period, you don't really need rest if it's light work. But if we're doing heavy, for example, draw a line up and you need at least, you need at least 30 and maybe even 50 minutes of rest.
That was 30-minute lunch now. Or like, now we really have to take 30 minutes for lunch every day.
That could be. There could be different reasons. I know in California, by law, they can only work so many hours before they take lunch. So, at some companies, it's like if you're paid hourly at exactly 9:59, you're supposed to clock out. Then the company will get in trouble if you don't clock out right on time or a little before. Like, you need to have so many hours. You can only have so many hours before you take lunch. So if you have less, that's okay. And you have to have at least 30 minutes of lunch. So there could be different reasons, but that might be one. So this is uninterrupted work. So you could go 30 minutes before you need a break, or even just 10. And this tells you what percent of that time should be rest. So the higher you get, you can see that there's more and more rest, because you're moving along this scale down here, and it corresponds to a higher level on the table. So here's an old school version of, I don't know if this guy's an athlete, but anyway, looks like he's on a bike, and they are measuring his maximum oxygen consumption. And that, come on. Maybe it was somewhere else I saw a graph. Okay.
Nomogram is the one right after, like, where you measure your iron levels. Go on slide 7. That's what we were talking to measure off of using this diagram with oxygen levels.
So what I'm thinking of is and I can't find, is a graph that it looks kind of like this, but generally this is as like the intensity increases, your VO2, well, not max, but your VO2 will kind of rise, and then once it hits your max level, like it's a straight line. You can't consume more oxygen. Your body can't consume any more oxygen, and that's where you start to get, anaerobic, where your muscles are producing energy and working without oxygen, and so they create lactic acid. This kind of testing is possible in a lab, but it's not really possible in industry. I mean, you can imagine all the equipment that has to be hooked up to somebody. You have to like have a researcher pushing a cart or something while they like go do their work. It's just, it's not possible. Plus, in most, not all, but in most cases, people are not reaching their VO2 max during work. So in the lab, it says highly motivated subjects. So you have to have people who are, I mean, you maybe you pay them well, I don't know, but they got to be willing to push it to the max. That's what you're trying to get. So, but so you're right about nomogram's method for estimating VO2 max, and it is fairly accurate. It's not the best, but I mean, this was probably produced in the era of slide rules, so the whole distances and stuff thing. Was that in 325?
Yeah, we were supposed to walk up and down the stairs and then take
Your heart rate?
Yeah.
Mm-hmm. Oh. So you guys are right. So you take your heart rate, and he's got it on two different sides for male and female. So based on your sex, you will find the corresponding side, also with your pulse, your heart rate, and then you'll find your weight on this side, also on the correct side of the line, and then you draw a line in between, and where it intersects is VO2 max. Again, probably the slide rule era before there were like calculators, but so you can get the VO2 max, but if you continue the line down, you can also look at work rate in watts, which is interesting. Yes. Yeah, I'm sure there are more complicated. Huh?
I didn't even think of that.
I think it's science has now, it can no longer just divide male and female. It now has to add in the other gender that exists.
Well, I think
we're still not comfortable, even going back to what we birthed. A lot of them still think that is incredibly discriminatory.
Even saying what you were birthed as?
Yeah, it's incredibly rude. And most, I won't say all, but a large portion of them still won't even identify that.
Yeah, I guess they just have to define things differently.
Sorry, don't mean to go on a rabbit.
No worries. We won't go too far down that hole. Well, so everyone is on a spectrum. So you can see, for example, his little tool. This is showing the accuracy of nomogram's tool, and this is within a plus or minus 10%. So most fall within that, but there are some that have a larger error using his method than others, and then you.
One of them's the elderly. So again, how many years have they been smoking?
And this one actually is so this is what it predicted, like 1.4, but this person was actually in better shape apparently than maybe they were real muscular. So BMI is something that someone's weight might be really high, but maybe they're like a bodybuilder, and so you might have a bodybuilder, and then you might have someone who's just really obese and their weight is the same. So yeah.
It's a huge thing. Like if you do yoga breathing, you're emptying out your lungs 100%. But most society, we only use 2 parts. We do them at the same time, so we're allowing more and more trapped oxygen in our lungs until we're like gasping for breath. If you practice yoga breathing, you're emptying your lungs 100% and refilling, which allows cleaner, more sustainable oxygen system. I love yoga. So
Interesting.
I'm gonna have to start doing yoga.
I love and adore yoga because it's that's why a lot of people say, "Oh, I feel so good," because you're emptying your system 100% of old oxygen. You're shoving fresh, clean air into every single part of your lungs.
Interesting.
Gotta get a DVD.
It's also good for strengthening your core. That's what I think about. But anyway,
Very much.
So yeah, I mean, I think if you were to develop a more accurate model where you didn't have to measure VO2 max, you might want to consider other inputs instead of male female. That are, I mean, so you might look at percent body fat, look at levels of, now this would be invasive and it would defeat the point of making an easy tool, but you know, like measuring testosterone levels, measuring hormone, estrogen levels. So I'm sure there's plenty of data you could collect to make a really accurate model, but at some point it starts to defeat the purpose because the model is supposed to make it quick and easy. Anyway.
Humans can't.
Yeah. Okay, so this is R, not R squared. So R squared is the term. I mean, it indicates the percent of variability that's due to what the inputs are. So unfortunately, if we were to square these values, it would they would be lower. So I don't know what 0.8, it would be like 0.6,
So what is
almost 0.7. You know, I'm forgetting R, but R squared is typically what, like in stats, what you are, at least what I'm typically interested in. To R squared is the percent of variability, or the proportion of variability that you're observing that is due to the inputs.
Okay, but that's not square.
Right, it's just R. So we would just have to square this number. And if you squared this, it would be, you know, 0.8 times 0.8 is going to be 0.64. So this is going to be maybe 0.7. So it's the proportion of variability due to his inputs in his model is around 70% for males. So there's still some room to improve. I mean, it's not a terrible R squared, but you know, for females, it's a lot better. That would be almost 0.9 maybe. You know, 0.9 times 0.9 would be 0.81. With the 7, it might be around 0.9. So 90%. So it's, with females, pretty accurate. And that's the actual equation, rather than using the slide rule, you know, setup. So for your assignment, wait. Oh, we're not using nomograms. Sorry, I apologize. We're using just Romerts. So for the assignment, you don't necessarily need this, but
We don't.
for the assignment, no. It's helpful to know about, though. Maximum heart rate. It's an estimate of the heart rate that you should not exceed if you're doing exercise. And that one's really easy. You just do 220 minus your age. So as we all get older, this number is going to go down. You know, there's less that we should do, at least in terms of our heart rate. But oh no, heart rate recovery.
Heart rate range.
Okay, yeah.
It's right
Why?
next door to you.
I was reading. There are lots. Yeah. I was reading about some others. There is heart rate recovery, which in occupational health is pertinent. But anyway, I was reading about some others, but there are multiple things that R could be. And yeah, obviously I mixed it up. So anyway, the percent heart rate range is there's another R that was used. But basically what this does is it tells you how much more you have to go before you hit your max. So if you are you measure your heart rate while you're doing some work, and you subtract the rest, and you take your max and you subtract the rest, divide this and multiply it by 100.
Yeah, we use that for the stairs.
Yeah.
It tells you how close you are to your max, basically. How much more room you have to go before you're maxed out. If we didn't multiply by 100, then I think maybe that's where I'm confused. Is I was reading about not the percent, but just the room in terms of beats per minute that you have left. Anyway, so that's interesting. Don't need it for the assignment, but this is an example of someone who's 40. If when they're resting, they're at 70, and then while they work, 110. Their max is 180, so they should never go above 180. And then their range is 36%. So at 110, they're 36% of the way to 180. All right, so Garg's method. This is what you are going to be using. Estimates energy expenditure. Other studies have shown that 5.2 is a good number. So you want to try to not exceed that too much. If you're doing this for workers that you oversee, for example. It looks at job characteristics and worker characteristics, and it looks at each task. And some of the things that we're interested in include all of these: force, frequency, technique, body weight, distance, posture, gender, and time within each task. The end result is the metabolic energy expenditure for that job. Well, let's just get onto. Oh, that is not showing up right.
Oh, it doesn't even show up right on our slideshow.
Really, in the PDF.
That's from me.
I don't remember. Wait. Yeah, mine pops up.
Okay, well.
This is PDF.
So here's the PDF.
The PowerPoint. My PowerPoint slides are showing me identical.
Can I? That's okay.
Oh, so it is supposed to be weird like that.
Well, some of it is weird, but what it was converting one of these to the ampersand, the and sign, and that's weird.
I think yours is fine. Yeah, it's just so E pause equals energy, T equals time duration. So it's just slightly skewed, but it's supposed to look like that.
So.
Yeah, it just looks weird.
So this is the summary equation. This is what you're going to use at the end. You look at the energy for all the postures, and you have to know how much time was spent with each posture.
What type of calculator would we need?
There's a bunch of scary symbols. It's just
Sigma is some.
yes. So you're going to take posture for task 1. Yeah, you're going to find the energy for posture 1. And then the time for posture 1 and multiply them together. Energy for 2, time for 2, multiply them together for 4 or more, and then add them together. So that's what this means, is just you're going to add them together.
Yeah, it's just a sum.
It looks scarier than it really is. Okay. Yeah. So you sum the energy for all the postures and you add it to the energy, the sum of the energy for all the tasks. Okay. So just break it out, and do it step by step. And, don't try and do it all in one step. It's not going to work. This is for the assignment. Yeah. And then, so you also have to, know the total time for the whole job cycle. So really, this will be just all the times added together will equal that. So like it takes 4 seconds for you to pick up the box, take it over there, and then come back, that sort of thing. Yep. So energy for the whole job cycle, energy for the position, the time in that, or posture, the time spent in that posture, the number of postures. It's really, are you doing 4 or 5 different tasks? How many tasks, basically, the way that I'm wording this, the energy for the task, the number of tasks, again, and then the, I guess you could have, you may have the same posture for multiple tasks. So that, this is probably more accurate. I'm just thinking of a task or a job where each task is a different posture. So
this is the example that Lexi read.
yes, yep. So we'll go through it. I mean, we're not going to do the math because it would take too long. It would, yeah, yep, it is. It would take too long as well. So some of the variables that we're about to see, and so I want to point them out. I'm not going to write them down, but we'll just try and remember. So F is the force applied by hands. G is the grade of the walking surface. So hopefully it's 0. I mean, if you want to make your task on a hill, then you'll have a number here. And if not, then it'll be 0. Okay.
Or you're watching setup stairs.
Yeah, that's a good point. And that would be a 50% grade. Yeah. I guess theirs might be something else, but I mean, if you're assuming it's a 1-to-1 for every foot you go up, you're also moving forward a foot, then that would be 50%. So H1 is the vertical height from the floor. Now, here's a key point. So if you're doing a lift, then it's the starting point. So if you're grabbing it from the floor and lifting the box up, then that's the starting point, and that's H1. So that would be 0 if you're lifting a box. But if you are lowering, it's always going to be on the floor. If you are lowering a box from a shelf, and that's your task, then that's H1. So H1 is always going to be basically the lowest point, and H2 is always the highest point. So if you're lifting, it's then the end point, and if you're lowering, then it's where you start. Does that make sense? So H1 is always lower or on the floor, and H2 is higher. L, think of it as the load. So it's the weight of the load in kilograms. S is the gender. So if you're doing it for you guys, you're just going to have zeros in there. For males, it would be 1, wherever you see an S. And then V, think of velocity. So that's the speed of just how fast are you walking. And I think, Dr. Fogelman is assuming about 2 meters per second for a typical walk. If, if your supervisor is watching you, you're probably walking faster. And if the supervisor is gone, maybe you're walking slower than 2 meters per second. But anyway, just pick a number that seems reasonable. It's not going to be like a sprint with a box or something. X, so think of that as like a point in space. So it's the horizontal movement of the workpiece. So are you walking, and this is all in metric. So is it like 10 meters away, 2 meters away? How far are you moving? And then T is the time. So we're going to look at each of the equations for each of the tasks. And if you have a task that is not covered in one of these, then pick a different task. So if you're climbing steps, this is the equation. So all you have is the body weight, which actually did this. Okay, I skipped over body weight, but BW is body weight. So all of these are for postures. Sorry, not tasks. So if you're climbing, sitting, standing, or standing but at an angle, bent, these are the different equations you'll use to find the energy. So these are pretty easy and straightforward. Finding the posture energy will not be that difficult. The tasks is a little more involved. So that's why I say just do it. Take it slow. It's just a matter of breaking it down and doing one little piece at a time. Organizing things so you don't get, if you need 4 pieces of paper, you have tasks over here and postures over here, and do that.
If I'm going to do that, yes, I want to be drunk.
No, you want to be completely 100% stuck.
I know.
So we're just supposed to kind of just make up a story of like, I'm pulling open a drawer, pulling a box box off a shelf,
Taking
putting
out
it onto the
trash.
floor, or putting it onto a cart and walking it out, taking it from the car and putting it on another shelf.
Yes, you can make up whatever job cycle you want.
Easy.
Yeah.
Keep it clean.
Yeah. Well, I guess whatever you want, but but as long as well, it's got to be one of these tasks. So anyway,
Maybe we should just meet at my house and we have to cup tea and discuss this.
so you can see. Let's take a look at just a couple of them. For a stoop lift, you're gonna need to know the body weight, H1, which is the lowest height of the box, whatever it happens to be.
Wait, we don't have to do all of these. We just have to pick one.
You will have 4 tasks, so
Okay, so
you'll
we have
have
to pick
4
4.
of them.
Okay.
And there's another page of them. There's 2.5 pages. Okay, so there are different tasks you can pick, but for the assignment you got to pick something that's on the list.
Yeah, no, that's much better. Because I was looking at all of them, like.
Yeah, you don't have to do all of these. 4 of them.
Okay, I feel better.
Yes. So this is the lowest point that the box will be at. So if it's the floor, it's 0. S. Do you remember what S is?
S is the gender.
The gender. So for ladies, it's going to be 0. So none of this is going to matter, right? And for males, it's 1. And then the load of the box.
Because that's just how scientists made it.
Well, you can see that. I guess that wasn't Garg's method, but for the larger you are, the more energy you're going to expend. And the more muscle mass you have, the more energy you're going to expend. So guys tend to be both of those. And so there will be more energy. There are some ladies I would not pick a fight with. But in general, on average. Yeah. So L is the load. So you can see everyone gets this term right here, 1.41 times the load, but then only guys get this one. Right. So you guys don't have to do that part. Don't even worry about that. So H2 is what?
H2, that's the height that you end at, and H1 is the height you start at.
If you're doing a lift, yes. So it will be the highest point that the box. So
Starting point for lower.
yes, yeah. So just think of H1. It's lower number. It's the bottom number. How far is it from the floor? If it's on the floor, it's going to be 0. Yes. Yep. So it should always be a positive number. Okay. You should never. We could change that and just make this an absolute value, but we don't. We won't worry about that. Also, you'll see after each of these, there's this sort of disclaimer. It's if the height 1 is less than height 2, and height 2 is less than or equal to 0.81. So you're not. Well, and this is meters, 0.81 meters. So none of these will work if your lift is more than 81% of a meter, 81 centimeters. Let's see here.
Which is on 15, and it's the third from the bottom.
Why are you making this difficult?
Oh, yes, you're right. You're right. Yep. So that could be higher.
So you're lifting your arms to pull said box off the shelf, and then you're lowering your arms.
Yes. Just keep these little disclaimers in mind when you're doing it. But you can see why.
Don't worry.
You can see why. So, because if H2 is more than 0.81, then this is going to become a negative number or 0, and that's going to mess up the equation. So, let's see. Want to check and make sure there are no other terms that we didn't cover. because some of these they have different things depending on what you're doing. I don't see any. Oh, here we do have some G and V, which are. I want to see if
G is great for walking surface, and V is speed of walking.
good. So any that are carrying or walking are going to have that V as well as the G term in there. But I think that covers everything. Oh, and then time. So the time that it takes to do that task for the lifts, we don't worry about the time. But for things like walking, then we do need to know the time, as well as holding.
Oh yeah, holding is a huge thing.
Yeah. So
That was another.
there's some more holding, and then pushing and pulling. And I know on the heat strain side of things that pushing and pulling are actually, they're more metabolically intense than you might think.
Oh, yeah.
So you can see that the numbers here might be bigger. I don't know for sure, but it'd be interesting to compare some tasks. Anyway, so that's the extent of the tasks that you can do in your job cycle. So pick 4 of those. And you're going to need some of these. I mean, so here's an example of a job cycle. And this is the example we'll walk through. Let's see, 10:25, right? Is when
Yeah.
so we got 15 minutes.
We can.
Yeah, we can. So we will lift this 20-kilogram box, carry it 10 meters at waist level, place it on a shelf that's 2 meters high, and then return with nothing to get another box. So the goal is to specify what the schedule should be for rest breaks. All right. So we're just going to break it down by tasks. The first one is to lift the box from the floor to your waist. So the floor would be 0 centimeters. Well, we're not quite there yet, but one thing we have to decide is this a stoop lift or a squat lift? And you can see which one uses more energy. That goes, I think I mentioned a game trail and how animals will walk.
Right.
Generally, I mean, not always. You can always find a game trail. That's, I'm sure, like it's like a bighorn sheep or something. Like, yeah, straight up the mountain. But generally, they will do whatever it takes to conserve energy, and that usually means just a gradual climb, even if it means 10 switchbacks, rather than what we do, and we just like to go right up. Yeah, just go straight up the hill. So, but this is just me. I don't have research or something to say this, but I believe that this is why most people default to the stoop lift, is because we're designed, we're wired to do what conserves energy, and the stoop lift conserves energy. So it's kind of hard to rewire someone's brain or train against that, and that's why it's better if you can find a way around that lift altogether, so that they don't have to make this decision, stoop or squat. But anyway, so we decide a stoop lift, and we decide that the waist height is 70 centimeters. So find your height, convert it to centimeters, and then just cut it in half. If you're going to do to the waist, if you're going to do somewhere else, like, I don't know, up higher, chest level or something, then make a reasonable guess at where that is. You don't have to measure it. Just, instead of 70, maybe 100 centimeters. Oh, wait. 100 centimeters is it's just 1 meter. So I'm thinking of, Yep. He was Shaquille O'Neal, like 2.5 meters tall or something, 250 centimeters tall. So body weight, and then we decide we're working with a female. So that simplifies some things, right? Some terms that we don't have to deal with. So the start of that, so H1 is 0. The body weight in kilograms was 55. L, which is the load weight, was 20 kilograms. And this is going to go away because we're dealing with a female. So don't worry about that. And then we have just the end height, or the highest height minus the bottom. Because at 0, that also makes that nice. So so if you want to make it easier, as many zeros you can put in your equation, the easier it'll get. So if H1 is 0, then it's just that number. I'd recommend when you're doing this, open up an Excel spreadsheet and just lay it out like this, or something, not exactly maybe, but something like this, or it could be exactly, I don't care. But that way you just have everything laid out. You just do one task at a time. And I'll show you what the equation in Excel kind of looks like for one of these. Also, the task time. So for the equation, we don't need the time, but if we go back to here, for the posture, we'll need to know what the time was, and also for the total time, we need to know. So just again, you don't have to time it, just make a reasonable guess at how much time it takes to do a stoop lift. So Dr. Fogelman has estimated 2 seconds. And that's, we have video of you guys doing it in about 2 seconds. So, and it would be nice to have this because I think it will need to be in minutes eventually. So that's one task. Second task, carrying it at waist level. So we'll kind of skip through this a little bit more quickly. But there are just some decisions that we need to make. What type of carrying it against the waist. So that's a specific task on that list. And the grade of the floor, generally it's going to be, if you want to make it easier, 0. And the walking speed, 0.5 meters per second. So you can imagine if you have a load, you're not going to be walking as fast as if you don't. And if it's against your waist, sometimes stuff gets in the way of your legs and you can't walk as quickly as you'd like. Yeah. So, but because we are walking, time does factor into this equation. Although this is a lot shorter. I'm guessing he's pulling. No, everything you need is right on this little section. So we have the time. We have the values for body weight, the grade, velocity, and the load. And that takes care of everything here. One thing, I'm going to go back real quick to verify what units the time in minutes. Yep. So it'll start out in seconds, and then you'll need to convert it into minutes. So in this equation, this T at the very end needs to be in minutes, not seconds. Units is important to keep track of. Make sure that the units you use are what the equation requires, because if not, it'll throw it all off. So place it on the shelf. We have no questions to ask here, but we have all of this to right. So we have subparts to this task. It's technically a stoop lift plus an arm lift. If you're just going then it would be just the arm lift. But because there's, you're engaging your pretty much your entire body, I'd imagine, then you have to add in the stoop lift component. So there are two parts to this, and you'd estimate each one, and then eventually we're just going to add the two together to get a single for the entire task. Is there anything new on this one? I don't think so. Another spot where, because the 0 for females, you'll just not have to worry about that. And then returning empty-handed. I mean, you guys can look up the equation, but you have to decide the walking speed, and 2 meters per second seems reasonable to me. You're not running, but a decent pace. So that one's pretty simple.
So I can just copy and paste these tables to our.
Yeah, I don't care. I don't care if you do that. Yeah. Yeah. So have a sheet that has like all the tasks maybe lined up on one side, and then put the postures on the other side or something. Organization can help a lot. So now, first thing that he's doing here is he wants to figure out that total time. So for task 1, he estimated 2 seconds, then 20 seconds to walk it over, 2 seconds to lift it up, and then 5 seconds to walk back. Now, when you estimate the velocity of the walk and the distance, you're going to have to use these to get the time. Does that make sense? So you'll estimate this and this. So what we did here is, if you look at that task 2, you could maybe write this down, but the time will equal the distance over the velocity. So you'll go 10 divided by 0.5. And we could look at the when I'm doing unit analysis, you don't have to do that for this, but we have 10 meters and then 5 meters per second. Then our meters are going to cancel out, and we're going to end up with seconds on the top, and that's what we want. It's just a way to keep track of your units and make sure they all line up and cancel out. You don't need to do that. If you just remember this, it's the distance divided by the velocity, you'll be fine. So you'll take the distance divided by the velocity, you get that. Same thing here. So he's estimating 29 seconds for one cycle. So we have the T. So one part of this is filled out. Now, let's see, yeah, he's doing the postures next. Is he? He is doing postures next. So it's all a standing posture. But if I'm going to go back real quick. These are the 4 options. So you're either climbing, step, sitting, standing, or standing bent. So it'll be, one of those. So for the postures, this is the postures alone. Okay, so this is how much time in minutes. That's not super clear on here, but does he mention that? Okay, here he does. So 0.48 minutes is the total time. And so we have the sum of the energy for postures times time. And it's standing times the body weight. So that's 1.32. That goes here. And then we multiply it by the time. So that is that. That's all that was. That big thing that looks scary. It was just that. Okay. Okay.
Tell me that when I have beer in hand.
So
I mean, now that it's got the numbers in there, yeah, it doesn't look that bad. But that.
if you take it step by step, then it's not so bad. And now here he's just pulling the numbers that he calculated for each of the tasks. So task 1, task 2, 3, and 4. You know, he did 2 portions: a stoop lift plus arm lift here, and then the walking back. So he's just adding all of these up right here. That's all that's going on. And then dividing by the total amount of time in minutes. Comes up with 7.2, which is kind of high on that 4 to 8 scale for the AIHA thing. But yeah, it's past the 5.2. So if you're above 5.2, then you know you need to have breaks. But now we figure out how many breaks, you know, how often. So you yeah, you compare 7.2 to a slide way at the beginning.
I did that yesterday.
Here. So 7.2, you look at this figure 816. 7.2 is very heavy right here. So we're going to look at this line. Come all the way back. So we go on the very heavy line, we go straight up, it crosses there, and we go over here, and we can see that according to AIHA, it was 81.5%, but here we need 55 to 80% and no more than 5 to 10 minutes. What's the correct? Uninterrupted work. So you can do that work for 5 to 10 minutes, and then you need to take a break. For 55 to 80% of that our time. Okay. All right. Thanks, guys.